Everything we've learned so far has been aimed at getting you into the groove of thinking logically so you can write computer programs that would solve real life business problems. We will now shift our focus from the general programming construct into the specifics of programming databases. While we were defining terminologies earlier in the course, we introduced databases by comparing the name with a military base. This was intended to demonstrate that data is housed in databases. Think about a database as the container for your data. Databases are created to support real-life business scenarios. Assume you run a school. It will be logical to have all data about the school in a centralized place. That centralized place will be the school database you will plan, design, and implement. Same goes for any business you can think of. There is an elaborate, well-developed data modeling process that goes into designing and developing databases, which we will talk about before the end of this course. But right now, I want you to recognize that you build your database around your central business theme. An airline reservation business may have a reservation database to house all data related to airline reservation. A grocery business may have a store database. A church may have a church database, etc. Remember that in building a database, your goal is to use the database to model your business so you can store your business data in the database. Let's create our first database. We will stick with our school example by creating a database which we will name school. To create our database, we execute the above command in a new query window. The syntax to create a database starts with the create database command, followed by the name we want to give our new database. In our case, we are naming our database school. So after the create database command, we add school and then tell the query engine that it's the end of the line with the semicolon. If we execute this command and refresh the database node of the Object Explorer, we see our new school database. In your database will be many database objects that will help in facilitating modeling your business. These objects include tables, views, functions, stored procedure, etc. The table in the database is used to model each individual entity that your business has. Remember, we said an entity is any tangible object, animate or inanimate, that participates in running your business. It could either be a person, place, or thing. This means that every noun that you can identify in a business will be a candidate for an entity. In our school example, we can identify two entities, which are students and courses. These two entities will be modeled in our new school database as a student table and a course table. Before we continue, let's discuss tables in general. A table is a two-dimensional structure made up of a vertical and horizontal component. The vertical component is called column, while the horizontal component is called row. Where columns and rows intersect is called a cell. Let's return to our school database. We identified two entities which we named students and courses. Entities like students and course have real-life properties. The student entity that is meant to model all the students in our school would have properties like first name of the student, the last name, etc. The course entity modeling all the courses taken in our school would have a course name attribute. Alongside these real-life properties, or what we refer to as natural properties, we can also add what we call surrogate properties to our entities. Examples of surrogate properties are things like the identification numbers given to students on enrollment. Identification numbers are unique to each student and ensure that no student is mistaken for another. Identification numbers are not natural properties of a student. Hence, we refer to identification numbers in this context as surrogate properties. We will also add a surrogate properties to our course entity as well. Therefore, we have a list of properties for both entities shown on your screen. The rules of data modeling states that each entity becomes a table and each property of an entity becomes a column in the table. Following these rules, our student and course entities become the student and course tables in our student database, and each of their properties stated above become columns in their respective tables. In database programming, when you create a table, you need to specify that table's name and columns. Let's create both the student and the course tables, starting with the student table. The code to create the table above oddly starts with a use command. Remember that we named our database school. So the use school command is essentially making sure that the table we will be creating below goes into the school database. The use command changes the database context to what is specified. You can always see the database context in the available databases drop-down in the Object Explorer. You can also change the database context in the drop-down list. When you do that, you don't need to use the use command. Right after the use command, we issue the go command. As we learned earlier, go is used to delineate batches. Finally, we come to the star of the show, our create table command. We see a trend here. When we wanted to create a database, we issued the create database command. Now that we are creating a table, we use a create table command. Therefore, it's logical to assume that whenever we want to create any object in the database, we issue the create command followed by the name of the object we are trying to create. Right after the create table command, we give the name of the table we are creating. Here, we are creating the student table. So we issue the command create table student. After this, we open and close a set of parentheses. Within the parentheses, you specify a comma-separated list of column names in the format column name space data type space nullability. The column name is the names from the property list, which is also displayed on your screen. Note that I have decided to use lowercasing for all my column names, but because you cannot have spaces between column names or any identifier in general, I have decided to use an underscore in place of a space to enhance readability. We will talk about different types of casing later. You should understand data types and what goes into determining the appropriate ones to use. You may want to refer back to our discussion on data types earlier in the course. What I would like to focus on here is the nullability part. Nullability specifies if the column would be a required column, which means there must be data in that column always, or a not required column, which means you can have data sometimes and other times the column may be empty. Nullability values could either be not null for required or null for not required. For now, when you see the word null, think empty. So not null will be not empty, which means the column cannot be empty, that is, it is required, or null will be empty, which means the column is not required from a data entry perspective. Following the column name space data type space nullability format, our first column is named student ID, followed by a space, and then the data type, which is char8 or ANSI fixed character column with length of 8. This is followed by another space and not null, saying that this column, student ID, is required. A comma separates each column except the last column, course ID, of character 4, char 4, and not null nullability. If you execute this command and check the tables node in your school database, you will see your newly created student table. Now let's create the course table. As we did earlier in creating the student table, we issue the create table command followed by the name of the table, course in this case, then add our comma separated list of columns in the parentheses following our column name space data type space nullability format. Go ahead and execute this code in a new query window. Inspect your tables node in the school database to ensure the table is created. If you do not see your course table in the tables node of the school's database after executing this command, right-click the tables node, click refresh, and confirm that you can now see both the student and the course tables. Well, congratulations. You have just created your first database and two brand new tables in the database. You will notice that when you inspect your student and course names in the table node, you see a DBO dot prefix before the name, such that you have DBO dot student and DBO dot course. The DBO part of the name is what we call a namespace. Think of a namespace as a logical container. In this case, you have a logical container called DBO, where we created the students table and the course table. Namespaces helps us to avoid something called name clashes, where you have two objects having the same name. We will return to namespaces when we have more experience working with objects in a database. I wanted to point out the concept here so you know why your tables have a DBO dot prefix. You will also hear people refer to namespaces as schema, that is DBO schema. Do not worry, both namespace and schema mean the same in database programming world. The period after the DBO namespace but before the actual table name is what is referred to in programming as the dot notation. The dot notation, widely used in programming, is used to denote that anything to the right of the dot is a child of what is to the left of the dot, forming a sort of hierarchical structure much like you would have in a family tree. Therefore, in the name DBO.student, DBO is on the left of the dot and student is to the right of the dot. This means that student, which in this case is our table name, is the child of DBO, which in this case is our schema. A more practical way to view this is to say that the table student, which is the child, resides in the DBO namespace or schema, which is the parent. You will see the DBO notation used a lot in your programming career, even outside database programming. Being familiar with it early on is very useful. All right, now that we have created our tables, we know why they are given the names we see in the database. We should try to interview our table to ask about any data in them. The command you have above is what we call a query. A query is a request for data stored in a database. In essence, whenever you issue a query, you are retrieving data to answer a question. Earlier, we were introduced to the select clause or keyword, and we said it is used to retrieve or display data in the database. Because writing a query involves retrieving data, the select clause is perfect for the job. It is also noteworthy to remember that the language that we are using to program databases is called structured query language, SQL. Let's get back to the command above. Our goal for writing this command is to retrieve all the data in the student table. We start with the select clause, which we all know is used to retrieve or display data. Then we have the asterisk symbol. The asterisk is what we call a wildcard in this context. It is a shortcut for displaying all the columns. Then on the next line, we have the from clause. The from clause specifies the table we are retrieving data from. In our case, we want the data in the student table. Therefore, our from clause specifies student. Regardless of the way we keyed in our command above using the computer keyboard, what we are instructing the database engine to do based on our command is, from the student table, which is the from clause, retrieve data displaying all the columns, select asterisk in the table. Make sure your database context is in the school database. If not, you can either change the context from the available database drop-down list or use the use school command. Run the query command. What happens? Immediately you execute this command, you see the results set section return just the column names of the student table, showing that the table itself is currently empty. Well, no surprises there. All we did is create the table. At no time did we add any data to it. This is a good spot to pause for a minute for you to catch your breath. In this class, we have learned how to issue the create command to create both databases and tables. We then learned the syntax to create two tables, student and course, in our school database. When we queried our table, it was unsurprisingly empty because we only created the table but did not add any data to it. In our next lesson, we will be doing just that, adding data to our table so we can query the data. See you in the next lesson.